Okay, part three. We're in the home stretch here, folks. All right, just gotta leg it out through this chapter, and we're good. So again, we're looking to derive the magnetic field that's generated by a straight line current carrying wire. And so let's set this up. So here is a wire, and it has a current. Has a current that is running upward. There's the current. And what was uncovered through lots of experimentation was that the magnetic field. Well, let me go back a second. Okay, let me go back a second. So you will recall that that the gravitational field strength is equal to capital G M over R squared, where M is the mass of the object in question, and R is the distance away from its center of mass. So one could determine the gravitational field by just literally plugging into this formula, knowing that G is the universal gravitational constant. Universal gravitational constant. Now there's a caveat here, right? So this is where this is good for R greater than the radius of the presumably circular object in question. Okay. If R is less than R, then we have to do a more complicated calculation. Okay. We know that E in magnitude was equal to 1 over 4 pi epsilon 0, magnitude of the charge over R squared. So we notice now that this inverse square behavior is something that nature preserves. And so again, through some experimentation, it was determined that the infinitesimal magnetic field strength was equal to mu naught over 4 pi I ds, and we'll get to what these are in a second, sine of theta over R squared. Okay, this can be written in a more elegant fashion. So mu naught over 4 pi. This is going to be I ds vector cross R caret vector, which is a unit vector in the radial direction, over R squared. Okay, and then this time this is a vector equation. So we're anticipating that this R squared behavior is, again, prolific in physics. And so experimentally, remember this is experimentally determined, again from, well, not exactly experimentally determined. This is obtained through the universal law of gravitation. And we got to this by equating the universal law of gravitation to what we called the weight, right, or the gravitational force phenomenologically. We got to the electric field, again, by way of Coulomb's law, which is, again, an experimentally determined relationship. And this relationship, which is experimentally determined as well, is called the Biot-Savart law, French, okay? Biot-Savart law. So let's go back and look at what we're after here, right? So we're looking at determining the magnetic field strength at point P, a distance r away, okay? And this wire is very long, right? Infinitely long. It goes from negative infinity to positive infinity. Again, building our coordinate system so that this is the origin, all right? And so we have an infinitesimal chunk of current here. We're going to call this ds, okay? And then we will call the distance from this chunk of current to the point in question here r. We will have a unit vector here, which is going to be r caret, unit vector r caret. We'll call this angle here theta, okay? And the magnetic field at point P, using the right-hand rule, right, is going to be sometimes I don't like when that circle is going to be into the plane of the paper, okay? So dB is into the plane of the paper. Okay, so I think we have all parameters here, except for the distance from the origin to the small chunk of current. Right, that distance is s, and then this distance is s plus ds. Okay, so there we think we have everything now that we need. Okay, so I just want to make sure we got this. All right, beautiful. So now, keeping this diagram on the page for as long as possible, we know that B is going to be the integral from negative infinity to positive infinity, dB, where dB is a function of r. Okay, and so this then will be from negative infinity to positive infinity. This will be mu naught over 4 pi. This will be I times the sine of theta ds over r squared. Now, we could have done this derivation a couple of ways, and I'm just going to work out the details of the one that's in your textbook. Now, so hopefully all of you see that symmetry is important here, because if we took a little chunk of current from here at the same distance r, hopefully you would see that there's a symmetry there, right? So there's a symmetry here, okay? So what we can do is we can just take this integral, and instead of going from negative infinity to positive infinity, we can just multiply it by 2, going from 0 to infinity. mu naught over 4 pi I sine of theta ds over r squared. Now, just to drive home the point of where this comes from, right? So remember, in a cross product, right? So we know that that involved a cross product of ds cross r caret, which is the magnitude of ds, magnitude of r caret, sine of the smallest angle between them. That gives the magnitude of that cross product. So the magnitude of ds vectors, ds, the magnitude of r caret, which is a unit vector, is just 1, and sine of theta. So that's where this piece comes from, okay? So we know where everything comes from now. So again, going back, we'll try to keep this figure up, as I said, for as long as possible. I'll cancel these 2's here at some later time, but let me just get down a couple of important geometrical relationships. So r is going to be the square root of s squared plus r squared. Again, looking at this triangle here, right? So looking at this triangle. Okay, beautiful. And we know that sine of theta is going to be the sine of pi minus theta. Okay. So, so if we look at this angle in here, which is 180 degrees minus theta, or pi minus theta, right? That's going to be equal to the sine of theta as well. Okay, so and the sine of theta, looking at that triangle, right, is going to be equal to r, capital R, over the square root of s squared plus r squared. Okay? So now that integral becomes then, these 2's are going to, this 2 will cancel with that 4, giving you a 2. Is going to be mu 0 over 2 pi times I. They're all constants. It's going to be 0 to infinity. So it's going to be r over s squared plus r squared. Actually, let me just back up here and just do this, right? So this is going to be, this will be then ds times the sine of theta. And the sine of theta then is going to be then r over s squared plus r squared to the 1/2. And so then b is going to be then mu 0 I over 2 pi, 0 to infinity. This will be r ds over s squared plus r squared to the 3/2 power. Okay. Okay, I might be missing a factor of r squared here. So 0 r I think we're okay. Yeah, I think we're okay here, right? This is okay. Yeah. So if you you can pull out the r. Let's just take it one step at a time. So this is mu 0 I times r over 2 pi, 0 to infinity, 1 over s squared plus r squared this would be ds to the 3/2 power. So this integral, you can just look it up. It's actually in an appendix in your textbook. But this integral then is going to be equal to the following. It's going to be 2 pi. It's going to be s over r squared, s squared plus r squared to the 1/2 power, and that'll go from 0 to infinity. So one of these will cancel one of these. Okay, and so what we need to look at now is the limits on the integral. So this is mu0 over 2 pi r. So it's going to be s over s squared plus r squared to the 1/2 power between 0 and infinity. So 0 is easy. Okay, so when s is equal to 0, then that becomes 0 over r, and so that's going to be 0. But we got to look at the infinity piece. Okay, so what I'm going to do now is I'm going to take out an s squared. So this is going to be an s squared 1 plus r squared over s squared, all this to the 1/2 power. That's going to give you s over s 1 plus r squared over s squared to the 1/2 power. These cancel, and so then this is going to give you 1 over 1 plus r squared over s squared to the 1/2 power. And so in the limit, as s approaches infinity, 1 over 1 plus r squared over s squared to the 1/2 power is going to be equal to 1 over 1 plus 0, which is equal to 1. Mathematicians would cringe here, but that's the limit as s goes to infinity. So then what we have here then is b is equal to mu naught I over 2 pi r. We have then 1 minus 0 when we take into account the limits of this part of the integral. Okay, and so that's just going to give you mu 0 I over 2 pi r, and we've derived that. Okay, awesome. So this is the magnetic field for a straight line current carrying wire a distance r away. Okay, so let's end there, and then I will pick it up in part 4.